Alright, I think that was a little too fast. Let's start over. This is Carhab Solutions, a machine learning senior project by these students. I'm this one. And this is a self-driving vehicle. For our project, we wanted to develop a novel implementation of self-driving. Rather than the traditional lane following, we used exclusively traffic signage to define point-to-point navigation. This is obviously not how humans drive on public roads, but it is applicable to small-scale autonomous vehicles, such as inventory management systems. In this application, using signage to define vehicle paths would be more modular and easier than painting out lanes for the entire path. We accomplished sign detection and classification using a custom-trained YOLO V5S model. YOLO is a machine learning algorithm that stands for You Only Look Once. This refers to the fact that the algorithm performs only a single convolutional pass to determine all detected classes in an image, instead of spending multiple passes refining region proposals and classes within those regions. This approach is less accurate, but significantly faster, which makes it a necessity for real-time processing. So the vehicle can identify signs, but how does that translate to driving? That brings us to this program. This is the state visualizer. It's used to help communicate what driving state the vehicle is in. I use the word state because our driving algorithm for a vehicle is a state machine. This is what the standard generalized state machine looks like. The memory delivers its current state to the combinatorial output logic, which then generates the output for that cycle. At the same time, the next state logic uses the input data from that cycle to determine the next state. The following cycle, the process repeats, and the new state becomes the current state. This is what our state machine looks like. We have two states instead of one, and our input data is fed into the next state logic and output logic blocks. Our final output is vehicle control code, and our inputs include state time, trackers, and depth values. Despite this, the control code actually isn't an especially complicated state machine, but it can be difficult to tell what the vehicle is thinking at any given point, so it's helpful to visualize. Which brings us back to this program. The first row of red rectangles represent navigation states. These are involved in the approach and execution of destination signs. Okay, so what are destination signs? Destination signs are the basis of this vehicle's point-to-point driving algorithm. They represent navigational instructions that define the path of the car. These signs are approached, then at a certain depth executed, allowing the next destination sign to come into view and direct the car. So, for example, if I wanted the vehicle to trace out an S shape, I would place the signs like this. Back to the state visualizer, the second row of pink rectangles represent modifier states. These affect the speed and timing of the instructional output of navigation states. Stop signs stop the vehicle for 2 seconds, forward signs multiply approach speeds by 1.5, and caution signs add a 0.1 second delay between the approach and throttle instructions. Finally, the two orange output rectangles describe the instructional output of the function. Only two outputs are sent per main loop execution of the driving logic state machine: the string instruction and the float amount. The instruction can be throttle, with amount representing speed, or directional, with amount representing degrees. When a navigation state is unselected, it will be red, and when selected, it will be green. For modifier states, the corresponding colors are pink and yellow. A state will only have its state time beneath it if it is the currently selected state. This is because only one navigation or modifier state can be active at any given time. To be clear, a navigation state and a modifier state can both be active concurrently, but two or more modifiers or two or more navigation states could not. Alright, we've covered the left side of the screen, but what's going on here? This is the debug view of the main driving function. All of the factors that determine the next state output are visualized here, as well as some other useful stats. First, and most importantly, are the trackers. Using a YOLO V5S custom-trained model, the detected and classified traffic signs in a frame are converted to trackers with unique IDs through the use of the sort algorithm. These are represented by green bounding boxes in the debug view. Next up is depth. Currently, depth values from an Intel RealSense camera are being overlaid onto the frame. This range of values is represented by a blue to green gradient, with green representing close distances and blue representing far. Obstacles past the minimum braking threshold are represented by red. The bounding box that is checked for depths used to detect obstacles is represented by a white rectangle in the frame. The minimum point of depth within that bounding box is represented by a yellow circle, the value of which is printed in yellow above the rectangle. If the depth measured is below the obstacle threshold, the rectangle will become red, indicating that the car has entered the obstacle detected state. A similar system is used to visualize the sign depth. The centroid of the bounding box's depth is printed in green, while the minimum depth within the sign's bounding box is printed in red. The value which is appended to the sign's tracker and used for state logic is the red value. Moving to the bottom row, it seems to be mostly self-explanatory, but let's check anyway. Looks good to me. Now that we know what we're looking at, let's analyze some driving. The car begins in the initial state, indicating it has not yet detected a sign. Very quickly it notices the left turn sign and draws a bounding box. Since the sign is off-center to the left of the frame, the car enters the centered left state. In the centering states, wheel angle is proportional to the distance of the tracked object centroid to the center of the frame. The car then begins accelerating, adjusting between center right, center left, move forward, and center pulling. During this time, the throttle applied to the vehicle is proportional to the depth of the detected sign, so that as the vehicle approaches, the car slows down. Once the depth of the left turn sign is below the execution threshold, the vehicle enters the left sign state to turn its wheels left, then the directional sign pulling state to apply throttle until a navigation sign with a different tracked ID becomes visible. The new navigation sign, representing U-turn, becomes visible and the vehicle stops turning, now entering the centering states to approach. The process is repeated, except now that a forward sign is visible, the throttle is multiplied by 1.5. Let's see how far the vehicle can make it around this course. I'd say that's good enough for a proof of concept. Thank you for watching, and if you're interested, the GitHub repository for this project is linked below.